Okay.
Observational talk.
Great, thanks.
Good afternoon.
So yeah, I was going to give a different titled talk, but then I saw Dirk's talk on Tuesday morning, and we're basically going to discuss sort of the same thing. And because Dirk is such an eloquent speaker, and he already pretty much said everything I wanted to say, I pretty much decided to change my talk at the last minute, and maybe just focus a little bit more about these last couple of years, which I actually find quite interesting right now in the Arctic. And then I'll talk a little bit more about some of the thoughts that I have about climate models towards the end. But you know, I mean, as we all know, the Arctic sea ice has been shrinking. Our lowest extent, of course, occurred in 2012, and this is just a spatial plot of where the ice was in 2012. I mean, nothing really special happened last year. I mean, we were tied for the second lowest minimum extent, but when you did the monthly average, it actually was not remarkable at all. And where we are right now, nothing too remarkable is happening. So why do I think this is such interesting times? Well, one of the things that gets less attention is the fact that the winter ice is starting to respond more as well. So the last 3 winters, this winter and then the 2 prior to it, had the lowest maximum extents on record. And where we see most of the treat has been mostly happening, of course, in the Kara and the Barents Seas, is where we seem to have these larger treats. But of course, the winter changes are still much smaller. It's about half the rate of change, about 43,000 square kilometers per year compared to about 87,000 square kilometers per September. But you know, these changes in winter are starting to become more noticeable. But if you actually start looking at even closer, and I just look at standardized sea ice extent anomalies over the satellite data record, we had, from January 2016 to April 2017, we had 16 consecutive months where the sea ice extent fell more than 2 standard deviations below the long-term mean. And, you know, we never saw this before. I mean, certainly we had times when, you know, like of course in 2007, we had quite extreme sea ice extent, and we've had other times where we had maybe a few more months in a row where you would keep these anomalies, but we never saw anything like what we've had over the last couple of years. And even though May once again went back up a little bit, wasn't 2 sigma below the mean, certainly, actually this should be June to August, we're also more than 2 standard deviations below the long-term mean. So there's a real shift happening right now in the Arctic, where these anomalies that we're seeing in summertime are persisting now throughout the other months of the year as well. And I started looking at this and just looking at it maybe going back further in time, depending on how much you trust our ability to reconstruct sea ice extent further back in time. We released, at NSIDC, they released a new sea ice extent data record that goes back to about 1850, where they've tried to infill some of the missing data from other ice charts and whaling reports. Things like that. And if I also do a standardized anomaly plot, we see that there's periods where we had a lot of negative or more sea ice in the earlier record, and then of course what's going on right now is quite striking in this longer record. And even, you know, when you look at this other times when you've had periods of less sea ice in the 1950s or even in the 1930s, you still never had such persistence of really large departures from the long-term mean. And just to show this a little bit more, if I just look at a Hofmahler of sea ice extent anomalies by year and by month, you know, we look at these anomalies that we're starting to pick up, actually even before the satellite data record. If we look at the full data record back to 1850, we're starting to pick these up already in the 1970s. And then it's really here, sort of the 2000s, where now these anomalies are extending throughout all calendar months in the Arctic. I can also look at breakpoints. I know Dirk mentioned in his talk this idea that there might be 2 different trends. If we do breakpoint analysis from this long-term data record, we find actually in October we have, we started picking up a breakpoint around in the 1990s that was significant at a p-value of 0.01. And then also if we look at January, February, and August, September, October, we also have significance at the 95th percentile. But even here earlier in the data record, if we start looking at these other months or in summer where you don't think we have such big changes, if you do some breakpoint analysis trend, it's suggesting that things started to shift even before the satellite data record. So then, it's been interesting. I've been working with Ingrid a little bit up in Norway, and so we have a paper that's under revision right now. And just trying to break things down maybe by region a little bit, because obviously total sea ice extent isn't that informative as to where the changes are happening in the Arctic. And then one of the things she was looking at is looking at regional trends. So we're just breaking up the Arctic by different regions, so the Central Arctic Ocean, the Canadian Archipelago, the Beaufort, Chukchi Seas, and of course all the seasonal zones. And you can kind of start looking at defining what we call the summer mode, which is where you don't really have any change in winter. Those regions are fully ice covered in winter. And so the trends are really focused mostly in the summertime, and the largest trends, for example, on the East Siberian Sea. But you can also see some of these regions are starting to have trends that are extending maybe a little bit more to the shoulder season. And then you also have, of course, your winter mode, where you don't have any trends in the summer sea ice cover because it all melts out anyways. And so you have sort of these winter mode areas. But one question that you might ask as you're starting to transition towards perhaps a seasonally ice-free Arctic is what zones might start to transition first from a winter mode, for example, maybe to a summer mode. And if I look at the LAPTEP-C, the trends are actually starting to go down a bit in the summertime, and they're starting to get larger sort of at the edges of the melt season. So maybe that this zone could be what we might look at next as sort of transitioning more towards a winter mode. And so she discusses this more in her paper. I didn't want to go into too much details. But when I was thinking about these anomalies and how the fact that we've had 16 consecutive months with the sea ice extent more than 2 standard deviations below the long-term mean, obviously, if we're starting to get an increase in variability, I was questioning whether or not this indicates that we're starting to have this transition towards a seasonally ice-free Arctic. And it's something we certainly use in ecology models where you can look at changes in variance and maybe applying a system change is about to happen. And of course, I'm also interested in this in the context of seasonal ice forecasting, because if the sea ice is becoming so much more variable, it makes it that much more difficult for us to forecast a few months out what the ice cover is going to be. So I started looking at this just over the satellite data record. And so here I'm looking at sea ice extent anomalies, just the anomalies here in the gray, and then a 10-year moving mean in the dark line. And then looking at a 10-year moving variance on the detrended anomalies. And if you look at that, you see this really large increase in the variance that we're starting to see around about 2007. And so that was kind of curious to me that we see this massive increase in variance. If I were to break it down by month and just try to see, well, where do I see this happening? We don't really see much happening in change in variance in the winter months. There's not much happening at all. But in the summer, we start picking up some increase in variance, for example, in the 90s in the summertime. But then in September and October, we start picking some up also later in the time series. And then again, in the wintertime, it goes back to very little change in the variance. And so one of the thoughts I was thinking, well, maybe this increase, for example, in summer in the 90s, maybe could have related to some changes in atmospheric circulation patterns, which I'll discuss in a moment, and then try to think about what could be driving this maybe in September, October towards the latter part of the data record. And before I do that, I just wanted to also show spatially maybe where we see these changes in variability. So this is looking at trends in 5-year ice concentration variance. And it looks as you would probably expect, right? So in the more southerly regions where we keep losing the sea ice on a regular basis, especially in winter, the variance is going down. So maybe your ability to forecast in these regions would actually go up because the variance is going down. We pretty much are losing our ice. And it's actually more toward sort of here in the Barents Sea, where you're starting to get an increase in winter variance. Same in the summertime. If you look at like August, September, October, you get this big increase in variance that's moving now towards the Central Arctic. But if you look at the outside of that, we're actually seeing reductions in variance. So it gives us some idea too, like if you're thinking about forecasting, maybe you can do a better job in these regions and where it's all blue because the variance is actually going down over time, whereas in these red areas it's getting more challenging because the variance is actually increasing. So my first question that I had was, do I see something in the climate system that could sort of match these increases in variance that I was seeing in the sea ice extent data record? So I was looking at different things. I looked at annual mean air temperature anomalies north of 70, the monthly mean air temperature anomalies, the relative vorticity, the NAO and the AO index, and also the seasonal variable NAM anomalies, just to see if there was something there that could maybe correspond to what I'm seeing in the observations. And nothing really clear stands out from this, I don't think. I mean, definitely there seems to be this increase in the 90s that might be related to the NAO, that would maybe have helped increase some of the variance in the summertime. But we don't really see, except for with the AO a little bit here towards the later part of the record and the NAO, that maybe there could be some influences there on the latter part of the variability changes. However, when I looked at this in the historical record and I decided to compute, again, this moving variance, so detrended data moving variance, using the 1981 to 2010 baseline, that increase in variance completely disappeared. So it was no longer there. And it made me think, well, first off, I thought, well, maybe there's a problem with this data record, because we know it's spotty. There's a lot of infilling happening. We don't know the observations of total sea ice extent for the Arctic. I mean, it's based on some limited observations. There's a lot of infilling going on. So maybe that could explain why we get these big, large increases in variance, for example, in early 1900s, also around 1950s. But then what I discovered, if I played around with different baselines, the idea of how the system is changing was very different. So, for example, if I looked at the 1981 to 2010 baseline, so that's the one we have here, we don't see these increases in variance in the latter part of the data record. If I use the full 1850 to 2013 baseline, then I do get this big increase in the variance at the end. We still have an increase here in the 1950s. And also if I use just an 1901 to 1930 baseline, again, we get this huge increase in variance. And so it's very sensitive to the baseline that we're going to compute these anomalies relative to, and then we're going to compute the variance relative to. And so one thing that we realize is that this large variance, for example, in the earlier part of a data record, is mainly because the seasonal cycle back then was so much smaller than it is now. And therefore, it's going to give us very large anomalies, and hence very large variance when we're trying to look at this over the longer time period. And so we can see, for example, and there's different ways to compute seasonality indices. I'm just using max minus min divided by annual extent just for this one. But if you look at a seasonality index, I mean, there really wasn't much happening, in the early part of a data record, but certainly in the satellite data record now, we have this huge increase in seasonality that is starting to look a little bit more like what we already see in the Antarctic. And so it's actually this signal that I'm really picking up when I'm looking at computing changes in variance over time for different baselines, is the fact that this seasonality has also been changing over time. And so that's going to then really influence our interpretation of how we see whether or not the variance is increasing. And so maybe another approach would be to actually compute a running baseline over time rather than just computing a baseline over the full time series, but trying to pick up how the seasonality is changing over time. And when you do that, then you get a different expression of how the variance is changing over time with regards to the sea ice. There's still something happening here in the 1950s. I don't know if it's real. I don't know if it's an artifact of the data set. I think we have to be really cautious in using this historical data set. But I thought, well, okay, do I see this by chance also in the climate models? Do we see similar features in the climate model simulations? Excuse me. So I'm just going to show a couple examples just from a couple runs. This is one from MPI. And so just to orient you a little bit here, this is the sea ice extent. This is for the historical 1850 to 2005. There's a running baseline. Actually, it doesn't really show up very well on the screen. I'm sorry about that. Actually, it shows up really strange on the screen. Anyways, but here's the seasonality index that's computed over time. Actually gets a huge increase in seasonality also in the 1950s. And this is looking at just how the anomaly is relative to the full time series as a baseline versus doing a running baseline. And then if you look at that, this is what how your variance has changed by computing the anomalies relative to the full time period or having a running baseline that's always changing with time. And so you do see to pick up sort of these features that are at least consistent in this one in terms of this increase in variance in sort of in the like 1930s, 1940s, and then again in this time period. But certainly, in this case, the increase in variance really closely is tied to the increase in seasonality that we see in the model. We can look at CESM, and same sorts of results are shown. I mean, you have different patterns. So these seasonalities are all different between the different models in terms of their time period. But here's another example where they do show consistency, at least something else happening kind of in the 1940s and then happening again here later in the data record. But here, if we do the running mean baseline versus just the anomaly baseline, we do get this decrease in variance that's happening later, kind of goes down a little bit, so it's not quite as pronounced. And so in this case, the increase in variance does decrease quite a bit using the changing baseline, and not so much maybe in the other model run I showed. But overall, just looking at all of the individual climate model runs, They do agree with the observations that the change in the variance is mostly a result of a change in seasonality and not the increase in stochastic behavior. So I think that was one interesting thing to look at. And just I could show just one more if I just look at the multi-model means from RCP 4.5 and on then RCP 8.5, so going out into the future. We have this increase in seasonality that just keeps happening over time. In RCP 8.5, it does start to go down after you lose the summer sea ice, but the winter ice is still decreasing. But the big increase in variance that you see, if you just do it relative to the full time period baseline, completely disappears when you use a running baseline. Okay, so now I wanted to talk a little bit more about these last 2 years, because I do find them quite interesting in terms of just how anomalous the sea ice cover has been. And I just thought I'd show a couple things first. So one is that this is a new update of Arctic Circle temperatures, and this was not done by climate scientists necessarily. It's done by Berkeley Earth, which is this independent climate fact-finding group where they're trying to provide more objective evaluation of temperature changes. It was actually originally, I think, brought together by the Koch brothers to try to disprove that global warming was happening. They actually came back and said, yep, global warming is happening. So this is their latest analysis of what's happening in the Arctic. And then they rank all of the years as a function of the warmest year. So 2016, in their record, is the warmest year that they have seen during the time. And actually, the 10 warmest years have all happened in the last decade. So we're definitely amplifying change right now in the Arctic. And we've also looked at the fact that, well, these last 2 winters have been quite warm in the Arctic. I know Richard Kolither published a paper, and Overland did as well, talking about how warm winter 2015 to 16 was, and how we had quite a few warm cyclones that came into the Arctic, bringing a lot of warm, humid air that helped bring temperatures at the pole above 0. That happened again this winter. And in fact, if we look at the freezing degree day anomalies, this year was the most anomalous out of all the years, and even compared to the 2015, which is the one here. So we had a lot less freezing degree days than normal. And if we look spatially where those happened, in 2015-16 winter, it was really focused over in the Barents Sea. And there were a couple papers looked at sort of how that could have impacted the ice. There was one by Ricker et al. That looked at how this might have impacted ice growth in that region. Lynette Boisvort also led one looking at how it impacted the energy balance at the ice edge here and maybe led to some of the decrease in sea ice. But this year, or this winter, these anomalies were pretty much widespread. They covered the whole Arctic Ocean. I mean, they were still focused here in the Barents Sea, but they also stretched across the pole and over in the Chukchi Sea. Looking at what impact this had, or just even before the freezing degree days are calculated, just looking at what happened with the freeze-up, this is a map of the anomaly of the freeze-up for 2016. This is from passive microwave data. And we see pretty much freeze-up was delayed pretty much everywhere in the Arctic except for a little section right here. But definitely over here in the Chukchi and the Beaufort Sea, freeze-up was delayed by about 3 to 4 weeks compared to the long-term mean, which I do 1981 to 2010. And over in the Barents Sea, it was delayed by about 2 months. So we had huge delays in the freeze-up. So what I wanted to do then was look at, okay, so we know that this last winter was also very warm. What impact did this have on winter ice growth? Did we see changes because we had so few freezing degree days? And I guess one of the problems is, I'm not sure yet, do we trust the current ice thickness observations to address interannual variability? Can we say with confidence that this year we would have had thinner or thicker ice relative to other years? And I'm just showing November thickness anomalies from CPOM, AVI, and NASA. So this is from Nathan Kurtz. And this is for all the areas that are shown in color in this graph. And actually, I was pretty happy to see this, that if I look at the average thickness anomalies from these 3 data sets, they actually are in pretty good agreement. In 2013, there's a bit of a difference with the NASA product compared to the other 2. But I would say, you know, at least the direction of the anomalies, whether they're negative or positive, is largely consistent between these products. So that was encouraging to see. Spatially, they're also generally consistent. So if I look at the thickness anomaly for 2016 this November, they all show that there was thicker ice north of Greenland and the Canadian archipelago, and thinner ice sort of here in the Beaufort Sea, maybe a little bit thicker ice over here towards the Laptev side. And they all sort of show the same pattern. The NASA product does show a little bit of a deviation from that, where they do have this area here in between north of Ellesmere Island where they actually don't show a positive thickness anomaly. And their negative thickness anomalies are they're stronger than you get from the other two data products. So there are some differences, certainly spatially, into the magnitudes of how they differ. So what we decided to do, and this is doing work that I'm doing with David Schroeder and Michelle Samaros and Danny Feltham, was to look at using these observations, but also combining them with SICE model runs to better understand, you know, how did thermodynamic ice growth change, how much did the thickness change based on dynamical influences, and how robust are these results by comparing with the other satellite products. So I won't go into details about how David does the SICE runs, because I know that's part of his talk, but this is basically our result if we look at the April 2017 thickness anomalies this is from CPOM, AVI, and from NASA Nathan Kurtz's product. This is the SICE modeled anomaly, and then these are the contributions from thermodynamic ice growth, and this is a contribution from dynamical changes. So the first thing you can see definitely when you look at this is that all of these satellite products have now a negative thickness anomaly sort of here north of the Canadian archipelago in all of these, and SICE actually doesn't have that, which I found a little bit interesting. And if you go back just a second, they all had positive anomalies to start the winter season though, and then by April these were all negative. And I'll show something next about snow that maybe have influenced that, but otherwise they do kind of agree somewhat that you do have a bit of thicker ice perhaps this April, you know, according from the pole, maybe going towards Siberia. It's a lot larger in Nathan Kurtz's data product. We also captured that here in SICE, but SICE definitely shows this widespread, broad, low thickness anomaly sort of in the Beaufort Sea and the Chukchi Sea. And this is then largely, thermodynamic ice growth was really quite anomalous throughout most of the Arctic Ocean. There was this area north of Barrow where they had quite rapid ice growth and a lot of ice production. This is a region, according to observations, where they did have a lot of thick ice formation off the coast of Barrow. And then we can look at dynamical effects, and we definitely saw a lot of thickening happening in SICE here in the Barents and sort of Kara Seas. And we do know that this last winter we had a positive Arctic oscillation, so we would have had more export away from the coast of Siberia and down towards Fram Strait, which could be responsible for some of this ridging and rafting. And this is definitely an area this summer that didn't melt out very quickly. In fact, the ice edge in this region really didn't change much this summer, so it could have actually had thicker ice in this region. And definitely thinner ice from dynamical changes would also make sense with a negative Arctic oscillation. But I am puzzled by these negative anomalies that I see in all the satellite data products that we don't get from SICE, but SICE was initialized with this November CPOM ice thickness. So what exactly is happening in this region? And one thing that I'm not sure of is whether or not snow anomalies could have played a role. So this is the precip, the snow depth anomalies from SICE for all these different years. And definitely in April of 2017, you have a large positive anomaly in snow depth in that region where all of those observations are suggesting thinner sea ice. So that would be biasing their thickness observations a bit low. So maybe that could be one factor. I don't know though, because obviously I don't know how much I trust these snow depths from SICE to really make that assertion. But it is a bit puzzling why there's such an anomaly in that region where I wouldn't have expected. You couldn't have had such thermodynamic or dynamical changes that would change that anomaly so dramatically. How am I doing on time? Okay. But I just wanted to then talk a bit about negative feedback. So it might be counterintuitive, but I think most all of you guys do know this, is that, of course, if I look at ice growth over time, so this is modeled from SICE for the Arctic Ocean, and I look at winter air temperatures, so this is all from November to April. As the air temperatures have gone up, so has the thermodynamic ice growth. And actually our peak ice growth years were in 2007 and 2012. Of course, you had a lot of open water, so you had a lot of rapid ice formation. But it is interesting if you think about after 2012, air temperatures have continued to go up quite a bit in winter, and yet our thermodynamic ice growth is starting to drop off. So it does make me wonder if this relationship is maybe starting to change a little bit. This is a correlation between ice growth and air temperatures. And so there's certain regions where you have a positive correlation, more ice growth for warmer air temperatures, other regions where the reverse is true. So I don't know if that's spatial pattern.
Where's the ice growth coming from?
The ice growth is coming from from running ice, yeah. And of course we know, again, this is ice growth. So actually now this is just showing the mean ice growth over time from ice. And this is November ice thickness. And so certainly you do get more ice formation for thinner ice. So we do see that there's a good correlation between these two. But definitely the last couple years, I think that might be changing a little bit. But I think that we can't really say, I know PIMS has suggested that this April was the thinnest. We had the lowest sea ice extent. They suggested quite thin ice. I don't think we can really say that confidently at the moment, at least not from the cryostat thickness products. For some reason, Nathan Kurtz's is definitely an outlier this April. He actually shows a slight positive anomaly for the Arctic Ocean, whereas Avi and CPOM are in agreement that there's a negative anomaly, but none of them are as low as what we saw in 2013. So it definitely wasn't the thinnest ice this April compared to all the other cryostat years, but it might have been among the thinner ones. Again, though, there's this bias between these estimates, so it makes that a little bit less certain. So then, of course, we have our summer. It's been actually quite an unremarkable summer. I still contribute to writing the Sea Ice News and Analysis post at NSIDC, and we have been quite bored about what to say about the summer because there hasn't been much happening. If I look at the timing of melt onset, so these kind of pinkish areas are basically no anomaly from the long-term trend, so our mean. So there was not really anything special going on with melt onset except here in the Chukchi Sea, which did melt out very early this year, had the least amount of sea ice that they'd ever seen in May in this region, and a little bit early melt onset in the Beaufort Sea, but really nothing remarkable. You look at the air temperature anomalies for June, July, and August, there's pretty much nothing remarkable happening. And so as a result, even though we started out this melt season with the least amount of winter ice, maybe ice that was on the thin side, but certainly not the thinnest that we probably have seen. We kept tracking pretty good with 2012, but then in August we completely fell off, and we'll probably be about the 8th lowest in terms of the extreme minimum at this rate.
How much open water there is within the pack on the top right? Is that the usual? The blue is like 50%, 60%?
Oh yeah, so I mean, again, so ice concentration, you have to be careful. I think now I could probably trust that a bit more because the melt pond should be freezing up by now. So usually in summer I would say I don't trust the sea ice concentration from passive microwave because it's going to think that melt ponds are open water. But I would say by now, with the temperatures dropping, I would trust this a bit more. And so it could mean that it's quite diffuse within the ice pack still. So even though the total extent is not that unusual, if you looked at the actual ice area, it might be a bit more so this year, which is it's a good thing I haven't looked at that actually. I usually wait because you don't want to bias it by active melt happening. But in September we should be able to probably look at that. And then I just thought I would show you results from the sea ice outlook this year. So this is the August outlook from all the different methods. So for those that don't know, the sea ice outlook solicits contributions of the forecast for September sea ice extent every June, July, and August using any method people want to employ. The median forecast right now from everybody is about 4.54, which actually would probably be pretty reasonable because today's value is about 4.64. Again, this is a monthly median extent, so we don't have that value yet until the end of the month, but they actually might not have been too bad this year. Which actually gets me thinking more about just seasonal ice forecasting in general, and I think it's really challenging. So this year was pretty much normal. I think the sea ice extent is just following the long-term trend this year, which makes it maybe easier to predict. But there's definitely years where we don't predict very well. So there's years when the observed September sea ice extent in red matches very well with the median of the predicted extents, which is here by these blue squares. And then there's years where the observed extent falls well outside the range of all the predicted values. And we've been looking at this since 2008. And the good news is, I guess, is that the median forecasts for July do still slightly beat linear extrapolation or persistence. So if you look at the absolute error, it's about 400,000 square kilometers, and it's a little bit more just extrapolation of a trend, but we're not doing a whole lot better then persistence or extrapolation of the linear trend at this point. So, 5 minutes? Okay. All right, so I'm just going to close with a few comments about modeling. Dirk already showed this plot in his talk. I think it's a really nice study because it does maybe help us understand. I mean, models are useful for a lot of things, and then Dirk touched upon that in his talk. But this is a really intuitive way, I think, for us to understand more when the Arctic may become ice-free, rather than looking at climate model projections and trying to decide, well, which climate model is better, how do we know it's going to give us the best date? We can just relate it directly to how much carbon we're putting in the atmosphere. And I think that's a really nice metric, and especially, I think, for policymakers to be able to say, okay, look, this is the kind of limit we need to have on emission rates if we want to keep Arctic sea ice in the Arctic basin. But everybody still uses climate models a lot, and they have been getting better. I mean, definitely, if I look at how well the CMIP5 models do compared to what CMIP3 did, and we look at the observed extents, and then we look at how well the historical simulations match that, they do a lot better than they did in CMIP3, and so I think that's encouraging. Obviously, there's a huge spread still, so it's very difficult, I think, at least from a policy perspective, to try to translate this huge spread and possible outcomes into a policy that is really useful. But I would also caution that we still get a lot of parts of the climate system in the Arctic not quite correct. So even though maybe we can get the trend and extent or sort of the seasonal cycle of the sea ice in the Arctic better, we still don't do very well at getting the thickness right. So if I just take the ISAT mean thickness and I compare that to the ensemble mean model thickness and look at the difference between the two, generally as a whole the models still get ice that's too thick across the pole and towards East Siberia compared to the observations, and they actually have too thin of ice over here in the Canadian archipelago and north of Greenland. And actually 3 climate models were able to get this spatial pattern correct. And out of those, one of them also didn't get the mean circulation pattern correct. So if I look at, simulating the Beaufort High and the transpolar drift stream, like CCSM4, for example, can't do the Beaufort High. So even though it gets the thickness distribution right, it doesn't necessarily get it right for the right reason. And I think we always have to be careful in how we use models, and I think about this in terms of CMIP6 as well, is that, usually when we evaluate models, we're sort of limited by our baseline of what observations we have available. So we make these assessments based on the observations that we have either from satellite or other data records, but that actually biases by a time that is maybe not relevant for the future either. So that calibration period is somewhat arbitrary. And one way to show that would be to look at the trends from 1953 compared to the trends from 1990 to 2013. And if you look at these trends, I mean, just because, so if you're in this box, that means you get the trends right from 1953 to 1990, and you get them right from 1990 to 2013. And so while many of the models can get the trend correctly for the earlier period, very few actually get the trend right for the later period. So if you're going to try to subselect models based on how well they're simulating some historical period that you're arbitrarily defining, that doesn't mean they're going to actually do good later in the future. So I think we have to be very careful with that. I also think that it really doesn't matter a whole lot. We did some just sort of random subselecting, oops, I should have done that, where we just took a random ensemble of 100 different ensemble members and just looked at the distribution of the timing of ice-free conditions. And this is just the multi-model ensemble mean, if you just take out models that actually do good compared to like the extent trends. And you can see it really doesn't matter a whole lot. So it's not going to change your timing of ice-free conditions that much by subselecting models. And since I only have a couple minutes left, I just want to end on maybe another way that we could think about using climate models. I did this study with Michael Rung that we published in Nature Climate Change last year. And he's looking at using models more for ecological systems, but just trying to come up, I mean, there's no one climate model that will ever best fit the observations at any one point in time. It's always changing. So one year one model may fit, another year another model may fit, but there's no set of models that's always going to get the system behavior right. And so we were looking at trying to take the climate models, and I'm just showing 10 just to make it easier to visualize. And we're trying to minimize the chaos statistic between the observed values from the observations and what the models are giving, and try to come up with the best weighted fitted model that would minimize the chaos statistics, so then use those perhaps to forecast what the sea ice would be like in the future. And this just shows that here, this is just showing the change in the model weights over time. So Like these red models maybe don't have much weight, or they have a lot of weight, but then it goes down over time. The blue models start to increase their weight over time. And so you're always changing how well your model fits the observations, but then you could take the fits at say 1979, 1988, or any of these years, and you can then make forecasts out in the future based on that model fit of how much sea ice there would be left. So if I use 1979 values, I get about 2 million square kilometers under the RCP 4.5 scenario of sea ice. If I were to use 2012 values, I get a forecast that's about almost 1 million square kilometers. So it just shows you how this climate state is changing over time and how you can maybe use these models to inform decision making over time. And it does suggest, and this is only through, this is only through 2014 in our paper, but I mean here we get maybe around 1 million square kilometers if we use 2012 to 2014 to make forecasts out to the future in 2080 about how much ice will be left. So this may be an alternative way we can look at using climate models. And I'm out of time, so I'll just leave my conclusions on the board. Thanks.
Thank you. Very interesting talk. Can we have some questions? Yeah.
What are the historical data? I mean, are you extracting sort of logs and like parsing? We've been back to the mid-1800s.
Yeah, well, so in the we can kind of go back to about 1953 pretty reliably, I would say, because there's a lot of earlier satellites and aircraft and ship reports. And then before that, it gets a lot sparser. So there's ice chart data from like the Danish, for example, and the Canadians. There's whaling log reports. So again, it's not, but that's not going to give you Pan-Arctic, right? So it's going to give you maybe a regional assessment in a particular area, and then you're filling in large parts of the Arctic. And so I'm really cautious when I try to look at, for example, the change in variability over the longer time period. Can I trust that data record? Because I might be having some artificial biases in that.
Maybe related to that, actually, we got a different sort of talk about infilling the circle from missing data. Part of the infilling was done by taking variant statistics from neighbouring data and using that to inform statistical model. I just wondered the extent to which sort of the infilling of data borrows surrounding statistics, in which case can you trust the variance that you're getting out of this infill data?
That's a really good question, and I don't know the answer to that, to be honest. I didn't actually work on the historical data set or put it together, so I'd have to go back and talk with like John Walsh who did that analysis. But that's a really good question.
Ian, would you like to come up, and if there is anyone with an extra question, I'm happy to take it while Ian's going. Yeah.
How reliable do you think the ice thickness data are when they're all from the same satellite?
Oh, for the cryostat?
Yeah.
I think it's a bit challenging yet to really use it